Yes, Naveen.
Yes, sir.
The control is yours.
Can you see my sharing screen here,
Yes,
everyone?
sir. Yes, sir.
Okay, okay, okay. Okay. So should I start, sir?
Yes, Naveen, you can proceed.
Okay, fine.
Okay.
Good,
Yes.
yes, sir. Good morning, students. So myself, I think I have my name. My name is Naveen Kumar, and right now I am pursuing a PhD in IISc Bangalore. Coming to my academics like background, I did my bachelor's from IIT Kharagpur in mechanical department, and then I went on to pursue my master's in IIT Hyderabad in manufacturing, and then I went on to do my job. Like I did job for 2 years in a PSU, that is in Heavy Engineering Corporation, Ranchi. So it's a PSU like BHEL and DRDO and all. So no, DRDO is not PSU. Fine. So worked there for 2 years. Then I thought like, so let me do a PhD. So then I got an admission into uh, IAS here, and right now I'm in my fourth. I mean, I completed my fourth year. I'm just in the starting stage of my fifth year. So it means that I'm in my final stage of my PhD. So and coming to GATE experience, I have been in this field for past 4 5 years. I'm
Sir,
teaching this.
one doubt, sir. Sorry for interrupting.
Okay.
How many years do we study PhD, sir?
Okay, fine. The PhD, the MHRD, I mean, the central government will provide you 5 years of stipend. So it will be a span of approximately 5 years. So you can complete before that. Sometimes, if based upon your problem statement, it might go beyond 5 years. Sometimes the appropriate time is 5 years.
Okay, sir.
Yes. Fine. So this is my pretty short introduction here. So I'll be handling complete mod section 4 in your GATE syllabus. If you go and see your GATE syllabus, you can see materials, manufacturing, and industrial engineering. So that's what I'm going to cover in this, lecture series here. So let me go here. That's what like manufacturing and industrial engineering, and today's your first class. So let me. I just want. I mean, as there are only three people here, I just want your introduction. Like, just tell me, please tell me your mention your name. I mean, I already have to see your name, but I just want to, what is your background? I mean, did you complete your B.Tech, or you're still in your third year, or you're doing some job, something like that? So here Dinesh is there. Like, Dinesh, can you uh, just give a little bit of intro of you? Like, where are you? I mean, what is your background? Mechanical, third year, or completed, something like that? Hello.
Yes, sir. Good morning, sir.
Good morning. Good morning.
Sir, I'm Dinesh. I'm from Salem. I'm
Okay.
completed my mechanical engineering.
Okay, fine. Good. So you are completed and just completed, and you're about, I mean,
Yeah,
you're
I'm passed in 2020, sir.
2020. Good. Fine. Good. Which college you are from?
Sir, I'm studied Hindustan College of Engineering Technology, Coimbatore.
Coimbatore. Okay. Good. 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 Okay, fine. So it means that you completed your B.Tech. It means that good. Next.
Yeah, I'm completed, sir.
Okay, good. Suraj, what about you?
Sir, same, sir. I completed BTech Mechanical in the same year, 2020, sir. I studied in VIT Vellore, sir.
Vellore. WIT. Very good. Excellent. Okay. Shiva, I think his audio is not available. Fine. Okay, fine. So this is like pretty much a short introduction, and let me close and keep the chat box ready so that if you want any. Give me 1 minute. Let's start the class.
So what's the weightage of this?
Yes, that's actually that slide is missing here. Let me put that slide. 1 minute. Give me one
Okay,
minute.
sir.
I'll
Okay,
just
sir.
put that.
Waiting, sir.
Actually, that slide is missing here. I'll just put that. Completely, I'll explain. Okay. Let me share some other slides and I'll come back to the originals, right? Mm, can you see the slides here?
Yes, sir.
Okay. So this is my intro. I just already told you this. Anyways, so this is your syllabus. If you go and see your section 4 of your this thing, let me oh, section 4 of your this thing in GATE syllabus, you can see materials, manufacturing, and industrial engineering. So we have these topics. You have engineering materials, and then casting, that is metal casting, metal forming, joining processes like welding. So these are the different miscellaneous, what you say, uh, manufacturing techniques. And the main important topic is machining and machine tool operations. Then we discuss metrology and inspection. Then if you integrate computer to the conventional machining and manufacturing process, that's called computer integrated manufacturing. So we'll be discussing this also. And going to second thing, this is your, this slide is of materials and manufacturing. If you see here, this is completely materials and manufacturing.
And MTM, no, sir.
NTM also. Manufacturing is like, manufacturing means like you have conventional and non-conventional. So that is what you're saying NTM, right?
Yes.
So this is what is this. And then coming to this is your complete industrial engineering. All this industrial engineering management is there, right? So this is your industrial engineering. And actually, I mean, I should have updated my syllabus. Here, what they have done, they've added one more topic in the year 2020, that is additive manufacturing. This is an addition.
Rapid manufacturing.
Yeah, rapid prototyping. Yes, rapid prototyping is another name for additive manufacturing. This is one extra topic that we have to discuss in coming, lectures. And here they have added one more thing, that is your lean manufacturing. So they have addition. This is your addition to your old syllabus. Lean manufacturing. And you can see here, here in metrology inspection, they have removed this gauge design. They removed this gauge design from the syllabus. That's what. So that's the pretty much, adjustment in the syllabus that they have made in GATE 2020. So in 2020 also, hope this portion, this syllabus will be maintained without any additions or subtractions. Fine. And I'm going to discuss this complete section 4. And coming to weightage, you can see here, this is complete. I mean, I've taken past, uh, 8 years of, I mean, data here, 9 years if you see. So you can see it's very important. I mean, very, very important. People think that this is not interesting. I mean, some people think that this is boring and all, but it's very simple and it's very, very, very easy. You have to struggle a lot to understand the concepts and apply that concepts to the questions and get to the right answer in rest of the topics like engineering mechanics, strength of materials, fluid mechanics, whatever it is. Okay, they seem to be interesting, but you have to have lots and lots of basics and understanding about your intermediate 10 plus 1 2 3 and all. So you have to have a very good aptitude skills to get to the solution. But manufacturing industrial is like little easier, but what you have to do is that you have to have little patience. That's what you have to do. So coming to that thing here, you have manufacturing. You see, almost all manufacturing plus industrial. You can see this 16 plus 5 is approximately 21%. This is again you have 21. This is 20, 20. So this is having 20. Approximately, you can say that on an average, you can get 22 to 25% of the weightage of the paper is from manufacturing and industrial engineering. Okay, so this is really an important topic and easy also. As we go through this complete lecture series, then we'll get to know it's very easy. Okay, the only thing is that you have to practice a lot daily, revise it, because you have to remember some things. It's not like derivations that you see in fluid mechanics or you know strength of materials. You don't have much derivations and proving things. But here mostly you have to remember things, and sometimes you should be able to see the things. Now everything is online. You can search whatever you want and see the operation in YouTube or some other video sharing platforms. You'll get to know the point. So that is what is weightage. So fine, let me stop this uh, screen and come back to the original slides that we have. One minute. Okay, fine. So today is class 1. So let's go little slow and let us get rhythm. Like you should come into my rhythm and I should go into your rhythm. So let's come on same platform and then we'll move together. So fine. So I just want you to, I mean, I just want this to be an interactive session so that it'll be very good. You don't lose your, feel there, because it's like online. You're not sitting in a classroom session. As you're in home, you feel that like you're alone. So I don't want that to happen. I just want to have this responses from you. And please, if you want to respond, put your speaker on, respond, then close it. Then I think you can press space bar to make sure that you can answer ask your question or answer something else.
Yes.
So yes, please, anyone can tell me what, I mean, by your definition, by your understanding of manufacturing, what is manufacturing?
Sir, is it okay if it is very general definition also?
It's very simple. I just want a definition where a simple layman can understand that. I didn't
Okay, sir.
Yes.
That is converting a raw material into
Okay.
finished goods is known
Yes.
as manufacturing. It's the
Excellent.
process where raw material is converted into
Yes.
finished goods.
Excellent, excellent, excellent. And that is the basic definition. Wherever you go, you see the first line of your manufacturing, they say this: converting raw materials into finished products. That's what. Who is this? Who answered this?
Me, sir, Suraj.
Suraj. Good. So it's the wise and good answer. Let's go. So see, that's what I've written here. See here, manufacturing is, in broadest sense, is process of converting raw material to valued products. That is what is finished product, valued. So at the end, it should have some value. You should be able to sell it and you should be able to use it, right? And how does the cycle go? So generally this cycle goes like this. So if you, sorry, if you see, we have this earth, right? We have earth, and then what you do, you just dig out your raw material from that, right? You, so who does this? Who does this digging of raw materials? Who does this? Which company does? Anyone?
Digging of raw materials is mining, you could say, in terms of gems, sir.
Yes, mining. So that's the reason. So you even mining. So like Coal India Corporation, you right? Coal India Corporation. So you have that company. So they do this. They dig all the crude raw materials and then they'll process it. So even if you are getting very good score in GATE, even Coal India also is offering jobs through GATE, right? So then what you do, you don't use that raw materials as it is. What you do, so these are in very crude form because everything is mixed and everything, right? So what you do, you process it, right? So what is this processing called? It's called metallurgical operations or metallurgical processing. So what you do, let's say you want a pure aluminium, right? Metallurgical operations, you perform some metallurgical operations on the raw materials, and then you convert raw materials into some, you know, uh, different, usable materials in the end. Usable, right? Now usable materials in the sense like you can use mild steel, you can use cast iron, you can use aluminium. That is what I'm saying, right? Now once you take this, you convert this raw materials. This is what is raw material, but you have this raw material. Now by using this manufacturing process, MP is manufacturing process. Now by using this manufacturing process, you get a valued product. You get a valued product. So are you going to use this product directly, or you are going to do something else before that?
Valued product, sir.
Ah,
I think we might machine it, design it, redesign it, refine it.
we do that, but why do you do this redesign? What is the reason behind the redesign that you're doing?
Because to get a proper dimension, sir,
Proper dimensions. How do you know whether it is a proper dimension or not?
we check it by
Check
gauge,
it.
the
It's
reading.
called inspection, right?
Yes, sir, inspection.
So you do that, you check that, right? Because you have designed something, right? So you have to check whether the product that you have manufactured is up to the designed one, right or wrong. So you have to do some inspection. Let me write it sideways so that you should not get troubled when you are reading the slides, right? You do the inspection. Now after this inspection, if it is good, then what you do, you use it. If it is bad or defective, so I'll write defective. I don't want to write bad, I'll just write defective. Then what you do, that is what is that redesign, right? So this defective parts will give you some feedback saying that, okay, your processing is wrong, so please do the processing right. Like it means that the material that you have taken is wrong, when the material is having some impurities in that. So you can give that feedback to processes. Sometimes it means that it happens that your manufacturing processes are not up to the mark, right? Because you might have some casting techniques or some machining techniques where you did not use proper machining parameters. So you did not get an exact product that you are intended to have. So you can give this feedback to the machining process also, right? And this feedback also can be done using redesign. That's what is called redesign. So you can do the redesigns, because it might happen that your design itself is wrong, or your design itself is having some problems in them. So that is what. So it's a closed loop thing, right? You started somewhere here. Let's say you started, I mean, raw materials. When there is a, so it's a closed loop. You can start from raw material. Okay, let me take this laser pointer. So you started from raw material. You're going to process, materials, manufacturing, valid product, inspection, defective, feedback. Then you're going. It is a loop. If you take this also is loop. If you take this also is a loop. So it's a closed loop, operations that is going to happen here. It's a closed loop control. I mean, if you know some controls, then it's kind of a closed loop control system, because if the in closed loop control system only we have this feedback. Okay, fine. So now coming to this picture here, depicts the, the what you say, the broadest sense of your manufacturing. So if you see, you have some, what is this? Can anyone say what is this? This diagram here. What is this? Can you, if you see, what is this? Can
It's
you
a
say?
nut and bolt
It's
joint.
a nut. It's a
Nut.
bolt kind of thing. Bolt.
Bolt.
And you can say bolt. Nut is like simply small nut. It's not
Small.
there here. It's a
Yes,
bolt.
sir, yes, sir, yes, sir, nut
It's a
is.
bolt, right? So now, if you want to make this bolt, you have to give some input, and you have to give some processes. Then only then output. This product will be coming as output. So can anyone say what is the input? What is the input? Anyone? Anyone? What might be the input?
The input will be the raw materials, such as the
Excellent.
material like
So
cast
correct.
iron, for
Let me write
example.
this. Material is one of the input. Any other?
Material. The tools required are the input, sir.
Machine, right? You need
Machine, yes, sir, machine.
right? Machine. So let me write machine here. Any other? Any other?
Material, machine. The processes such as measuring instruments, does it count?
All things come. Let us say all things are coming under machine only. Don't we want manpower?
Yes, sir, manpower.
Right? We have to have some person, right?
Yes, sir.
So manpower is important. So with these inputs, you have material, you have machine, you have manpower. It's called triple M. It's M, machine, manufacture, machine, manpower, and materials. It's called triple M. You need this minimum, basic. Once you need this, you convert this bolt. How do you, once it is having okay? So now you have to have some processes, right? So what is that process? What do you mean by process here?
The type that is required.
Manufacturing process, MP, right? Right. So which, so if at all I just want a bolt, so what is the manufacturing processes that you make use to make this bolt? Can anyone say, throw, how can you make it, how can you make this bolt? How, let's say I gave a simple, what you say, a block. It means that, like, I gave some, a block like this, simply a cylinder like this. How can you convert that in to this, a simple bolt? Can you, how do you do this? Which manufacturing process you'll use? Anyone? Have you ever seen a bolt making thing? Anyone? Okay, let me tell you. The simple one, it's nothing but, okay, let me, I'll write here, but I'll just rub it out. So what happens here is, you have this simple cylinder like this. Then what you do, you take this and put into your CNC machine, or lathe machine, lathe operation, and then you remove this piece, right? You turn it, turning, right? Anyone? Turning, right?
Yes, sir, turning
Yeah.
operation.
So turning, you remove this, you will get something like this.
Yes,
Right?
sir.
Remove
Yes, sir.
that. Now, after that, now what you do on lathe only, you do some threading operation, right or wrong? Right? So
Yes,
what
sir.
you do some threading operation here, right?
Yes, sir.
Right? And if you see here, you have some edges here. Can you see this part?
Yes,
Right?
sir. The
So what you
adjust.
do, you put that into a lathe machine. You put this into lathe, this milling machine, and then
And
you remove this part like this. Okay.
even might create slot also when necessary, sir.
Yes, if you want, you can take that out. So these are all the all what are these things? These are all manufacturing process
Processes.
processes, right? So selection of manufacturing process also is very, very, very important. You can make a product by using n number of processes, but which processes will make sure that your designed product is equal to the finished product? That is very important. Okay, fine. So let's erase this thing because okay, fine. Sorry, let me, because the slide should be clean and neat. Okay, fine. So that is what is this. Now, okay, what it encompasses of. So it encompasses design of the product. Obviously, you have to design the product. Selection of raw material. You have to select raw material because based. So strength of materials is done in your course is done, guys.
Sir, done, sir. Done, sir.
Yes, it is done. So now what do you do in strength of materials? You design or you size the materials, right? You size your products. So
Yes, sir.
you what you do, you tell the length of, let's say if you want to design a chair, let's say if you want to design a chair, something like that, right? So what you do, you say that the leg length should be so much, right? Because based upon the weight that a person is sitting, or you can say this chair is made for kids or adults or something like that. That is what is design, right? The design.
Sir, that's machine design, sir. We didn't study machine design here yet.
Fine. But machine design uses the principles of strength of materials only.
Yes, sir. That I know, sir. But
Right. You know, right?
yes, sir. The endurance strength, what strength it could go, the Young's modulus of the material. We study. We should know all that.
Yes. Right. So if based on the weight of the person sitting, what you see, you can size your, okay, my length of the leg should be this much, or my area of cross section of leg should be this much, A into B, like, right? And my base area should be this much. And should I have armrest? Yes, if I have armrest, what is that size and all? You do that by selecting some material, right?
And it also depends on this also, sir, whether it's static loading or dynamic loading.
Dynamic loading. Good. You take all these things, and that is what is called your design criteria. And selection of raw material is one of the aspect of it. Okay, and
Yes, sir.
the sequence of process through which the product will be manufactured. Sequences of process. Here, until unless in this product, if you see on this side, this product, when this diameter reduction before doing lathe operation, can you perform threading? Can you do that? You can't do that, right? What I'm saying is that before removing this material, can you do threading? You can't do. So that's the reason why the sequence of process through which the product will be manufactured is very important, right? Good. I mean, I see only Suraj. Is everyone okay? Suraj, come on. And there is Shiva and there is Dinesh.
Yes, sir.
Everyone is okay?
Yes.
Okay. Okay. Fine. So, okay, fine. So let me go into this. So this is what I mean. Again, I repeated the syllabus here. There I just showed a simple slide. Here I just repeated the syllabus. So in the broadest classification of engineering manufacturing process, we have casting. Metal casting is that what we are going to discuss today. Metal casting is one. In that, the casting is classified into two different categories. Those are expendable mold category and second is permanent mold category. What is expendable? What is permanent? We'll discuss that. But just to make a basic understanding, expendable molds are the molds we can't reuse it again. Permanent molds can be reused again. Again, I repeat, expendable molds cannot be reused again. Permanent molds can be reused again. It
So
means that
expandable molds means it can be reused and even reshaped.
Yeah, expendable we can't reuse like sand casting. Once you fill the mold cavity, you break the sand, right? There is no mold cavity again. Again, you have to build it, right?
Yes, sir.
But in permanent, you have some mold cavities with some metallic mold cavities. So you can't discard it. Again, you remove the clamps and all. Again, you join them. So you
Like
can
injection molding, sir.
injection molding. Good. You can reuse it again. Got the point?
Yes, sir.
Yes. So that are the categories. Based on those two categories, we'll be discussing the metal casting techniques. Next is your forming or shaping. In forming, what we have, in we have three different states like classification, like expandable and permanent. We have three different classifications. One is solid state, liquid and semi-liquid state, and last is powdered form state. Okay.
That is the sintered form, no, sir.
Yes, you have to do sintering at the end. Okay. So in solid state, we have forging, rolling, extrusion, drawing, sheet metal operations, etc. Okay. In liquid state,
Sir,
yeah.
you were not audible for some time, sir.
Uh, Now I think there's
Yes, sir, you were not audible for the last 10 seconds or something.
okay, fine, fine. Now I think my internet connection was a little unstable. Is it okay now?
Yes, sir.
Okay, fine. Is everyone has facing the same problem? The last 10 seconds had the problem? Hello? Dinesh and Shiva, are you facing the same problem like Suraj?
Yes, sir. Yes, sir.
Okay, now it is okay, right?
Now it's audible, sir.
Okay, thank you. So in liquid and semi-liquid state, you have casting, injection molding, and then etc. That are the things that we are going to discuss in liquid and semi-liquid state. And there is also one other thing called powdered form. That is your powder metallurgical process. So we'll be discussing this powder metallurgical processes at the end of the material science section, because after discussing materials, we'll be discussing this powder metallurgical operations. Okay. And the next category of manufacturing processes is, and widely used from past to till date and future also will be this, that is your machining. Widely used manufacturing processes is machining. So machining, turning, milling, boring, drilling, planing, shaping, broaching, grinding, all these things from uh, from here to here, as he mentioned, it is conventional machining process. Okay, conventional or traditional, they can say conventional MP. So please remember, MP is manufacturing process. Okay, and you can see from, let me change the color. So from here to here, these are non-traditional or unconventional. I'll write non-traditional. Non-traditional MP manufacturing process. NTMP they call. Okay. So these are non-conventional machining process. Okay. Fine. Now we'll be discussing conventional first and non-conventional second. In non-conventional, we have ultrasonic, chemical machining, electrical, electrochemical, high energy beam machinings. So I'll be clearly explaining you what is the difference between conventional and unconventional machining process. Sometimes you can call conventional as traditional and unconventional.
Sir,
Next, we have,
again we experienced a break, sir.
okay, why this is happening? Let me check my internet connection. Is it okay now? Am I audible?
Yes, sir, you're audible, sir.
Okay, fine. Fine. So joining process. So this is another classification of your manufacturing process. So what is it? The joining process, we have welding, brazing, soldering, and etc. So welding is a high energy source of high energy, high temperatures are required. For brazing and soldering, you don't need to have high temperatures, and you can join similar and dissimilar materials, and all these things we'll be discussing in joining process. And last one, that is what is your newly added syllabus, right? Newly added syllabus is your regenerative. It's called regenerative process, and that is your, you know, rapid prototyping, or sometimes it's also known as additive manufacturing.
Sir, so conventional and unconventional, we both will be studying, sir. And next is joining process again. Can you?
In joining process, we'll be discussing different principles of welding.
That
What
will,
the point?
yes, sir.
Like
Welding.
we have arc welding, gas welding, and all, right?
Yes, sir. Tungsten metal arc welding,
Yes,
tungsten
yes,
iron gas welding.
yes, yes. Excellent. We will discuss that. We'll discuss that, and the what you say, joining process field. Okay.
Regenerative process is only where we study that selective laser sintering, that thing.
Yes, we discuss additive manufacturing process. That's it. Like actually, I think
SLS, SAS, FDM.
FDM. Yes, we'll be discussing that. We'll be discussing that. LOM, laminated object modeling, and all. We'll be discussing them. Okay.
Okay, sir.
Okay. Fine. Next. So out of all these things, let's start the first one. That is your casting. Okay, sir.
So this is chapter
Yes,
1, casting.
chapter one is casting. We'll discuss the chapter one. That is your casting.
Why is it metal casting, sir?
Because we are going to discuss metal casting mostly. We will be dealing with metals. That's why I have written metal casting. Okay. Mostly we'll be pouring metals into that and do that. But in miscellaneous casting process, we'll be using some different materials, but mostly we'll be using metals that contains iron, Fe, right? So that's the reason why the topic I've put as metal casting. Okay,
Yes,
sir?
sir. Iron and steel mostly
Steel.
material.
Steel is derivative from iron.
Yes, sir. Alloy of iron and carbon.
Yes, yes. Fine. So now I need a definition for metal casting. I mean, at least a casting. Anyone knows what are the basic processes that metal casting is having?
Um, Sir, casting itself means that converting a metal or molten material into a solidified product. That is casting generally.
Fine. Good. So what we have is that I told you that manufacturing process is that what we have some raw material, and that raw material is converted into what? A finished product,
Yes, sir.
right? So we use this metal casting. By casting is used, but in casting what it does, you convert this raw material into molten stage, right? Molten state is what? Liquid state, right?
Liquid state. Yes, sir.
You convert that raw material to liquid state, and then you pour into something. It's called mold cavity. We'll discuss that. Some cavity.
Mold cavity. Yes, sir. Cavity.
And then you freeze it, right?
Solidify it exactly.
Exactly, you can say solidify. That is what exactly term is. Solidify it, and then you get the product, right?
We get a fair product.
Yes. We don't get a final. I mean, sometimes it can be a final product. Sometimes it might not be a final product. Okay.
Yes, sir.
Okay. Fine. Okay. So that is what is this. That is what is this. We can see here the process of pouring molten metal into a hollow cavity, okay, and allowing it to cool and solidify into a desired shape. That is what is our metal casting basic definition. The main important,
Cavity itself means hollow only, no, sir.
yeah, but obviously, but just to make sure it's like, it's a hollow cavity, they wrote it like that. Okay, fine, good. So the process of pouring molten, first is you have molten metal, then you have to pour into hollow cavity, and then you have to cool, allow it to cool, then you get this, then you do the solidification. At the end you'll get a desired shape. That is what is this metal casting. Okay, so the solidified product is called, the solidified part is known as metal casting or casting. Leave it about metal casting. So what are the industries that are very keen on using this metal castings? Those are automotive, where like we have, some
Piston.
automobiles, like Benz, whatever it is, all the companies of automotives use this. Cookery, it means like where you do the, pressure cookers and all stuff, will be using this metal casting techniques. And of course you can see aerospace industries like, Hindustan Aeronautics, ISRO, Boeing, all the companies, aerospace industries will be using this metal casting. And railways is known for it. Actually, railways have huge amount of, and there is, what is, where do you do this? There is a name, there's a place where all these castings are done. What is that place called? Anyone?
Sir,
There's a, if you go to workshop, I mean, if you go to any place, all these castings are done under one roof. And that,
foundry shop.
yes, yes, I need that name. It's foundry.
Sir, even ship industries also use casting, no, sir. Ship
Yes, man,
industry.
yes, yes. That's why I put etc here, so you take all the things into that etc. Okay. And jewelry also is used. So in jewelry you use some miscellaneous casting techniques, slush casting and all you'll be using there to get a very complicated shapes to the jewelry. Okay, fine. So you can see here, this is a basic understanding. I mean, if you can understand the basic diagram here, it is like you have a cavity here. So this is your, I mean, you see, this is your complete cavity. And how do you create this cavity? You put something inside, some, some kind of same thing here, and then you put sand, and you just make sure that sand is, tight here, and then you remove that something. What is that something, I'll ask you. And you create a cavity here. Once you create a cavity, you pour some liquid metal into it. Once you pour liquid metal into it, you allow it to solidify, and you get the casting out of it. Solidified part is known as casting, hence you get the casting out of it. Okay, so if you see, this is simple, simply you can see a simple casting. But you can't simply pour as if, as like you bring water and you just pour it, because molten metal is very hot, and it is having so much of heat in it, and it is having some problems if it is interacting with air. And if you're directly pouring, the sand may come and mix into this. There are so many problems. To avoid such kind of problems, what they have done is they have put this gating elements. They are called gating elements. Gating elements. So these are gating elements. Like you have some pouring cup here, you
Sprue.
have some, down sprue here, you have runner here, you have riser here, you have, this is your metal casting. So you, what is this? This is your core. This core is used for creating hollow sections, like hollow in the sense, if you have a hollow cylinder like this, if you want to create some kind of hollow cylinder, so we have to use a core. Don't worry about that core part. I'll tell you that clearly what is core, and we'll design that. And you do this thing into two different boxes. Those are called drag box, and another one is called coke
Co
box.
co box.
The coke box is the top box, and drag box is the bottom box. Sometimes even they use three boxes. Okay, they use three boxes. Let me draw that diagram. So they use three boxes. Can anyone say what is the top box? If they're using three boxes, top is scope again. So top is scope box, they can call. Bottom is drag box, they'll call. Can anyone say about the middle name? Anyone?
Sir?
The middle box name?
No idea, sir.
Cheek. It's called cheek. Okay, it's called cheek. But generally they don't use every time. Generally, 95% of the time they use this uh, two box molding techniques. That is your cope and drag. Top is core, bottom is drag. Okay, so we use these gating elements to make sure that your molten metal is going to enter your cavity on right time with proper amount of fluid flow, and make sure that your mold cavity is full. You have to make sure, because you can't see, because it's completely inside, hidden inside this cavity is completely inside the sand particles. You can't see it. To make sure you fill this cavity completely, you will be using this gating elements. The main gating element that will be used is riser, to make sure that your cavity is completely full. Right, we'll be discussing all these things. We'll be discussing how we are going to design the pouring up riser, runner, the sprue and core. All these things we'll be discussing. We'll be doing some math, and we'll be designing them. Each and every element of gating this element will be designed. Okay.
Sir, gate, I think you missed gate here, sir. Is gate that?
It's called in gate. I didn't tell that, but we'll discuss it. Huh? So let
Yes, sir.
me rub this nonsense so that the diagram is clear. Mm, Let me put it like this. Let me read this. Okay, now slide is clear. Okay, fine. Let's go to the next slide. Okay. So now, what are the advantages of this, you know, uh, metal casting? There's lots of advantages, but there are a little more. What you say? I mean, on an average, you can say how advantageous it is, and it will have some more disadvantages also, because it's not very easy to control the process parameters of metal casting. So let's see what are the advantages first. The first advantage is complex shape of object can be easily produced. It means that if you go and see, what can I say? Mm, have you ever seen an engine block of a motorbike? Engine block of a motorbike?
Sir,
Anyone?
engine block of a?
Motorbike.
I think I've seen, sir. Just can you explain, sir? Because
Just, I mean, I think it's like, if you go and see, you have some, fuel lines, passing it. It's kind of complete engine. It's very, very, very complicated.
yes, sir.
You see that?
Yes, sir. It is very
Have you
complicated,
seen
sir.
that? Yes. That complicated object, if you want to manufacture by machining, it's very difficult, right? You have to go, you have to keep slots, you have to make that, you have to do drilling, you have to do boring, you have to do that, you have to do this. But this complicated object can be manufactured by using casting in single go. Within one single go, you can manufacture this. So let me write that example. So example here is your engine block. A very complicated block can be easily manufactured by using metal casting. That is what one of the advantage. Another is, it is less expensive, because hardly you have to use a furnace to boil or heat the metal to become into the molten stage, and then you have to use some basic sand and some basic, what you say, the patterns and all, and it's a little less expensive. The power consumption also is not much here, so hence the casting techniques are less expensive process. And the main advantage, and as this is less, when as this is less expensive, we can use this product for mass production. Mass production is means what?
Um, you could use it for producing 100 products continuously,
Thousands
or
of
1,000 products
products
continuously.
we can use and produce this by with thousands. You can sometimes lakhs also will produce if they're small elements. Thousands of the products will be produced. That's called mass production, not mass production. Mass production. Okay. Next, ductile and brittle materials can be produced. So that's what. If you want this ductile, can anyone say which is soft, which is hard? Is ductile soft or hard?
Ductile is hard, sir.
No.
Sir, but ductile, no, sir. We ductile and brittle only matters on how how much the endurance strength is. That is how much it can withstand strain. That is only ductile or brittle, no, sir.
Generally,
So ductile is soft. So my mistake, sir. Ductile is soft.
soft,
Brittle is hard.
hard.
Once broken, they can't be.
Yes, brittle is hard material. See, you can produce a soft material, you can produce a hard material, right? So this ductile and soft hardened materials will be can be produced by metal casting, but this will be produced by controlling cooling. By controlling cooling only we can see whatever you can see that like it
Here,
is
directional
cooled.
solidification only
Yes,
will
by
happen.
controlling you can say solidification is one of the nice word. By controlling solidification only we can get both ductile and brittle structures. Okay, I'll tell you if you do fast cooling what will happen, if you do slow cooling what will happen, what is happening to the grain size, what is nucleation, all these things I'll be discussing, don't worry. Next is large size object can be produced by casting. Large size means a huge ton. If you, I mean, when I worked in my company for 2 years, when my ex company can say, when I can see even a 400 500 tons of product has been manufactured by using metal castings.
That object itself weighs 450 tons.
Yes, object itself is for 400 tons. It's very heavy. They use a very big cranes to lift that, and they do the
Yes.
castings. It's
So
very
in that case, they will have literally a basement full of sand, no, sir, for that.
no. They use I mean what you say sections of where they have a huge electrical ramming sections there. It's very good to see that, but unfortunately you can't see that because that's not. It's a very confidential thing because those are used for mostly for defense applications. Okay.
Sorry for the curiosity, sir.
Okay, fine. But in internet, you can just try a heavyweight metal casting processes. You can see that some of the processes are very. You can see a very big trucks and cranes moving that objects here and there. It's really visually wonder to see them. Okay, fine. Anyways, let's go come back. Next is um, limitations. Obviously if you have good there is some bad. So what are that? So casting objects are not having smooth surface finish, right? Because what why you're not having smooth surface finish? Because let me change the pen here. Yeah, why you're not having smooth surface finish? Because if you have this casting, right, this is your thing, this is sand, right? This is completely sand, right? Am I right or wrong?
Yes, sir, sand.
This is sand. So once you have this sand particles here, so obviously there'll be some dents forming onto this part or right or no?
Yes, sir, and that's why we even give pattern allowances also because of that.
That we'll discuss. That we'll discuss because of this sand particles attaching or I mean sticking to the part, you're not having a very smooth surface finish. So what do you
Sir,
do? You
mm,
take this part out of it and you do grinding. You do grinding and you get the product to the appropriate surface finish that you wanted to have. And second is here it is very laborious because nobody wants to work. If you go and see most of the engineers or most of the workmen, the labor and the the skilled people or unskilled, whatever it is, they feel I don't want to go to a foundry and work because it's dirty, one, and two, it is very laborious. Means you have to lift weight, you put that there, you bring that, you have to do ramming. It's the physical work is mostly involved during this metal casting process. If you go to a simple workshop with a lathe machine, this the guy simply stands there and he'll just rotate that simple spindle and all these things, and he'll do simply change that workpiece and simply put the tool and sit for some time. But in casting and foundry, the laborers have to work round the clock to make sure that you get a very good casting. So it's very laborious. Next is there is a possibility of casting defects, obviously, because you're dealing with liquid metals. If you have small mistake, then small mistake is enough. That's it. What will happen? You Some air particles will be trapped inside the casting, and or sometimes your liquid metal will be interacting with the environment, right? And oxygen is a very bad player in this, right? Because every liquid metal is tending to have the oxygen will try to attack this liquid metal, and it will oxidize, and that will make your product very defective. You don't want that to happen, so you have to make sure that oxygen is not interacting with this.
Sir, even there is another chance of casting defects, sir. Since directional solidification takes place, there is also a chance of India of the product to break if not checked properly.
Yeah, that's what you have to make sure that. We'll see that how we are going to do that. Next, castings are not having uniform, no, not having uniform mechanical properties due to non-uniform cooling. Well, because you don't have proper uniform cooling. Why? Because obviously, when you pour liquid metal into this, okay, this is your sand, okay? So this is your cavity. This middle one is your cavity. So when you pour liquid metal into this, from where your solidification starts, your solidification starts from the wall side, right? Right? Your solidification starts from the solid. So if your pouring temperature is some T1, let us say, if your ambient temperature is T2, right? Your temperature gradient, it's called temperature gradient, that is delta T, is T1 minus T2. As your temperature gradient is more, what will happen? You won't be having a uniform cooling. As you are not having a uniform cooling, the grain structures that are formed near the wall and in between the solid casting will be different. As the grain structures are not uniform, you don't have uniform mechanical properties. So those are the major limitations in metal casting. Okay, fine. So let's go. So how do you select a manufacturing process? When this slide I should have put before metal casting, but anyways, I'm just trying to explain it here. So you decide your manufacturing process by shape and size of the object. First, you see what is my shape. Okay, fine. Is it a rectangular, circular, hollow? What are the complications that are having? You see them. Then you see the size. Okay, you fix it. Okay, I'll use casting. Oh no, I'll use forming. Oh, I'll use machining, like something like that. Next, what is the complexity? Complexity in the sense, if you have internal holes, some tapering, something like that. How complex it is. Based on that, you'll be choosing your manufacturing process. Next, accuracy and surface finish. If you want a very good accuracy and surface finish, you have to use grinding techniques, right? So, like that. Next, how many products you are going to manufacture? So, you can use additive manufacture, and you can use 3D printing machine to produce whatever objects you want, but it's very costly, right? 3D printing is very costly. So you don't want that to be done in 3D printing. If at all, you can produce that so and so object using casting. Why do you want to go to 3D printing? I don't want that. So I can use casting techniques. Oh, I can use forming techniques. Wherever you have a cost less process, cost less, you have to minimize your cost, right? Next is what is the property required. So based on each process, your property of the object will be varying. So which method I have to choose to make sure that the property I want will be acquired. Okay, and of course, every time you have to keep cost in your mind, because it's going to make a huge profit or it's going to make a huge loss at the end if you're not selecting your manufacturing process appropriately.
Sir,
Okay.
so But is there any chance even by taking the cost also it might end up in loss?
By
Even by considering the cost also we might end up in a loss.
that will depend upon so many factors. Maybe the workers are not working properly. Maybe you don't have a skilled labor there. Maybe the management what they're trying to do is not proper. Maybe the machine is very old. You have so many problems in there, right?
Yes, sir.
You have to get a skilled labor. You have to update your machines. Everything is there, right? Yes,
Yes, sir.
yes,
Sure.
yeah. So let's go. So the next is pattern. Uh, okay, there is a chat coming up here. What is that? Okay, fine, good. Okay, fine. So what is pattern? Here you can see pattern is the replica of. What do you mean by replica? What is the meaning?
Um,
What is the meaning of replica?
Replica is like almost is exactly the same of
Copy.
the
Can you say
material.
copy?
Sir,
Copy of it, right?
copy. Yes, sir. Copy.
So pattern is a copy of final casting to be produced with some modifications. That modifications are these allowances, anyways. The modifications the are in the form of allowances. Okay, so let's say if you want to manufacture like this product, let us say, right? Like let me draw in the three-dimensional way so that it will be good to have look at it. So if you want to manufacture this product, let us say, okay, so exactly I'll make a copy of it, right? I'll just make copy, right? So this copy, so this is what you want to have, right? This is your metal casting. That's what you want to have, but you just copy it and make a pattern. And this is made up of different materials. Generally, it is made up of what? Anyone?
Sir,
Generally, this pattern material. What do you know? What do you know about pattern material? What are the
sir,
general
it can be wood,
wood?
wax,
Yes, it can be anything, but
even metal.
generally, I mean, there are so many materials. You can use plastics.
Yes, sir.
You can use metals. Sometimes you can use metals also, right?
Yes, sir. I know, sir.
Yes,
And
but
aluminum is better because of lightweight.
yes, light. So generally, wood will be your generally in sand casting especially. Okay, so you just make the copy of this metal casting and make the pattern, and the pattern is not exact. It's not having these two are not having exact dimensions, not having exact dimensions, because when you pour liquid metal sometimes the after while cooling it might shrink, and while removal by obviously you put the pattern into mold box and you ram it, right? You just put it into the mold box and you just ram that sand, maybe because while removing the pattern out of it you have some problems, and the sand is stuck to the pattern, that might have some problems. There's so many other problems. To make sure that you get an exact dimensions at the end, you add some allowances or make sure that you put some allowances onto the pattern, and that allowances are here. You can see there are 5 different allowances that are there in casting for a pattern. So you have first is shrinkage pattern, second is draft or taper pattern, then it is machining or finish pattern, and then allowances, so not pattern, allowances, and we have shape or wrapping elements, or the fifth one is your distortion and camber elements. So we are going to discuss each and everything in detail in the coming slides. So let me erase some stuff which is not very important here. Okay, fine. Let's go to that. So the first one we have here is your shrinkage elements. Okay. So can anyone, I mean, okay, 1 minute. I just want, if you have a material which is pure, let us assume that you have a pure metal, like you don't have any alloys in it. I mean,
Pure material.
pure material, a simple unary, it's called unary material. Let's say I have some unary material. Let me take a nice color here. Okay, this seems good here. Okay, okay, I want to draw a simple diagram here. So this x-axis represents time and y-axis represents temperature. Okay. So if I let me take different things again. So I take some point A here. Okay, and I can take some point. Okay, I don't want to take A. Let me. Okay, if I take some point A there, okay, and some point 1 and some point 2, it means that as time is going your temperature is reducing, right? It means that the temperature is in liquid state here, the temperature is in a solid state, because temperature is less, so this is your liquid and this is your solid. How does the graph look like? How do you make sure this, you join this line, how do you join it? Is a straight line, it is a parabolic line, how do you join these two lines if it is a pure metal? What is the profile of temperature with respect to time? Anyone? Anyone, sir?
Sir, can you repeat the question again,
What
sir?
I'm saying is that, let's say you have some mold cavity and you have poured liquid metal into this, right?
Yes, sir.
Now, liquid metal is this, okay? On the left hand side, this one, because the temperature is high, right?
Yes, sir. Temperature is high, it will be in liquid.
And as time proceeds, time is proceeding, right?
Yes, sir.
As time is producing, temperature is coming down, right?
Yes, sir. Temperature will come down. It's almost like the cooling curve, sir.
Cooling up. So what is, I just want to make you draw this cooling curve. Please draw the cooling curve.
It's
Tell
a
me how.
downward rectangular hyperbola, sir. Rectangular hyperbola.
So you mean like this?
Yes, sir. Like that.
Any other? Who is this saying? Who is talking to me here? Suraj, I guess. Right?
Suraj, yes, sir.
So Suraj is saying that it is a rectangular hyperbola. And what others want to say here? I mean, Dinesh is here. I mean, Deepak. Deepak is here. Shiva is here. What about, what are the comments from all the other guys except Suraj? Come on, only Suraj is answering here. I just want others also to be interactive. Please don't feel that your answer is right, wrong, good, bad. Nobody is going to care. Only thing is that you have to learn from here. And please, it is a request from my side that please be interactive. And as you know, an old quotation is that the failure is a stepping thing for a success. So if you fail only, you'll get to know the point. So please don't hesitate or don't feel shy, or maybe feel that, sir is going to feel bad or others are going to talk wrong about you, he's telling silly questions wrong. Don't feel that. Please interact with yourself, with myself. If it is blunder also, it doesn't matter. Please tell me the answer. What about Dinesh, Deepak, and Shiva? Is it a rectangular hyperbola, or you want me to join with a straight line, or what?
Yes, sir.
Hello, Shiva. Something you said, I didn't get that. Deepak, Dinesh,
Yes, sir. It's hyperbola.
rectangular hyperbola. Any other? Deepak,
No idea, sir.
no idea. Good. What about Shiva?
Yes, sir. It's correct.
So you're saying it is rectangular hyperbola. Okay, fine. But anyways, don't worry, and it's not a thing. So let me draw the real answer to you guys. The real solution to this is So the real means proper way to draw this is like this. It will come down in liquid stage like this. Then it will stop here. Then you have a straight line. Okay, let me draw. It's looking very bad. Like this. So this is your, so I'll write this as TP. TP means what? Pouring temperature. Okay, let me write them here. TP is pouring temperature. Pouring temperature means what? The temperature of liquid metal at the point of pouring. That's what is pouring temperature. And this will, so this is your liquid state. A is in liquid state. B also is in liquid state. But for certain time, there is no temperature change, but there is a heat reduction. What is this BC line, sir? Anyone? There is no temperature change. Anyone?
Sir?
This one. TF I can call. What is this TF temperature? At that temperature, you can see
Fusion
that
temperature.
phase transformation temperature. Can I say that?
Yeah.
Yes. It's called freezing temperature actually.
Yes, yes, sir.
Because at that time, your liquid is converting into
Solidification temperature would be the term, sir.
So solidification or freezing, anything. And this is your ambient temperature. Ambient in the sense?
Surrounding temperature.
Like surrounding temperature. Okay, guys. Understood the point? Okay. Now, let me take this point, D. Okay. So now, so what is this diagram? Let me, so this is nothing but time was temperature graph for a pure metal, or I can say cooling curve for a pure metal. That is also fine. Okay. So if you see, I can write this thing. What is AB? AB is complete in liquid state. Am I right or wrong? AB is liquid state, right?
Yes, sir. But one thing, sir, A to B, it won't be a straight line. It will almost be some slight curve.
That's true. That's true. That's true. But I'm assuming it to be a straight line. You're right. You're right. Actually, if you see, it'll go like this. Something, there is a dip also. That is a little complicated. I'm not going to discuss that. Okay.
Yes, sir.
Yeah. So AB is liquid state. And BC is what? Phase change. That's what is happening, right? Liquid
Yes,
to solid, right? And CD is what? Solid state. Everything is in solid, right? So from A to B, it is liquid, liquid to liquid, liquid to solid, liquid to liquid, liquid to solid, solid to solid. That's it. Solid, solid. That's it. Only temperature change. From A to B, there is a temperature change. And from C to D, there is a temperature change. But at BC, there is no temperature change. Without temperature change, that heat reduction is happening while this phase transformation is happening. Now, when you are pouring some liquid metal, will it have a shrinkage or will it expand upon cooling? If I have a liquid metal, I'm heating it, I'm pouring it into some cavity. While it is cooling, my question is, will it shrink or will it expand? Hello? Hello?
Yes, sir.
My question is, will the liquid metal shrink or expand?
It will shrink, sir.
Obviously, it will shrink, right?
On cooling, materials contract.
Yes,
Sol
most of the
so
materials contract.
solids contract on cooling.
Yes, right. So in liquid state, we have what is called liquid shrinkage. Here it is called liquid shrinkage. Okay, and during phase change, it's called solidification shrinkage. You have shrinkage, but there is a name for it. It's called solidification shrinkage, right? And during solid state, it's called solid shrinkage. Okay. Now, during liquid, now let us say you have some cavity like this. You're pouring liquid. So, when you're pouring, there is some shrinkage happening. Shrinkage means instead of fully shrinking, you have some shrinkage happening. So the left part can be compensated in liquid stage. How do you compensate this liquid shrinkage? Is called is by, okay, let me erase that. I'll tell you again. Here is, let me take different ink. Will it work here? Yeah, it's working. Okay. So out of these three, two of them, that is your first two shrinkages, will be taken care by riser. Don't worry, I'll tell you that riser part when we're discussing this riser design. And the solid shrinkage cannot be compensated by riser, but it can be compensated by a pattern. So why are we using pattern, sir? Guys, why are we using pattern?
To compensate solid shrinkage.
Excellent, to compensate solid shrinkage. So this is the CD, you can see, is compensated by what? Pattern. Okay. Okay. Now this shrinkage, whatever the shrinkage is happening, will be depending upon one parameter that is called alpha. And let me write that in a different ink here, green. Let me take green. So alpha is what? Coefficient of thermal expansion. Okay, so based on this value of different material, because you can pour aluminum, you can pour mild steel, you can pour cast iron, you can pour whatever material you want, but each and every material is having its own expansion and contraction. Am I right or wrong, sir?
Yes, sir.
Yes. So this, if your coefficient of expansion is positive, let's say, okay, then upon cooling you get, so I'll write here, upon cooling you get a contraction. So your liquid material will be contracting. If you have a negative coefficient of thermal expansion, upon cooling you get expansion of material. So it means
Is there
that
any material that expands on cooling, sir, generally?
yes, it's there. So gray cast iron, again I repeat, gray cast iron is a material which is having a negative coefficient of thermal expansion, where upon cooling it expands. Okay.
Yes, sir. Alpha can't be zero under any circumstance.
Alpha can be zero also.
Oh,
It can be
that is
zero
ideal.
also. No change. No change in the sense there is no expansion and there is no
Yes, sir.
contraction.
Is there any material with zero change, sir?
Yes, I think so. I forgot the name. Invar, I think so. Invar. I don't remember the name. I'll tell you that. Huh?
Yes, sir.
Yeah. There is no change. There is no. I mean, what you say? What can I say? No zero shrinkage. There is nothing. I think it is Invar. Invar only. I think so.
So most materials on cooling will contract.
Most materials. Okay. That's why it's called positive. Positive means what? If you're heating, it will expand. If you're cooling, it will contract. That's it. Okay. So with this, let me go and see the next slide. That is your uh, when the liquid metal is allowed. Then whatever the points I discussed here, okay, are have I've put down here in the slides here, so you can see that. When I'm just reading out, please let me if you have any doubts here, because whatever I've explained here, I'm just put down that things into the words in sentences. When the liquid metal is allowed to solidify, there are possibilities of contraction of material. Due to this, size of the casting will be decreased. Am I true? Am I true or not? Everybody with me or not?
Yes, sir.
Yes. When the liquid metal is cooled from pouring temperature to freezing temperature, from pouring temperature to freezing temperature, the shrinkage is called what? Liquid shrinkage. That is what I told. AB is called liquid shrinkage. Next, let me take a laser pointer to be useful for you. During phase transformation of shrinkage, shrinkage is called solidification shrinkage or phase transformation shrinkage. That's what is your what you say the B and C is your phase change shrinkage or solidification shrinkage. Next, when the solid casting is cooled from freezing temperature to ambient temperature in solid state, shrinkage, solid state is called solid shrinkage, right? So you can see CD is your solid shrinkage. Okay, let me write them A, B, B, C so that it will be useful for you. So this is AB, this is BC, line BC, and this is line CD. And liquid and solidification shrinkages are compensated by riser. Solid shrinkage is compensated by size of the pattern in the form of elements, right? So let me just move this up so that its elements is going its way here. Okay. 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 I think the slides are here. Let me go to another slides. Let me just open the new slides here. Okay. Can you see the slide?
Yes, sir.
Okay. So, okay. So these are the different materials with their what you say the shrinkage values here, right? So just to get a feel, no need to remember this, forget, just to make sure or to get a feel, I just want to show these values here so that you'll get an idea. Okay, cast iron is this much shrinking, Aluminum is shrinking this much, something like that. Okay. So if you see bismuth and inver, as I told you, bismuth and inver.
Yes, sir. So bismuth also comes in this case.
Yes. So bismuth and inver are having alpha 0. Am I right or wrong here?
Yes, sir.
Yes. And cast iron is having 10 mm of shrinkage for 1 meter. It means that if you have 1 meter of side, let us say for a cube or something like that, for 1 meter, if you're pouring liquid metal, it will shrink how much?
10 for 1 meter.
10 mm per 1 meter. Like that, aluminum will shrink 13 per meter, copper will shrink 17 per meter, steel is having a more shrinkage, that is 20 per meter, and brass is having 24 per meter shrinkage.
So alloy will have more shrinkage, sir.
Yes, you have this more shrinkage here. And please note that solid shrinkage is maximum for brass, which requires large sized patterns, right? Because if you want dimensions, let's say some L, I mean 1, 2, something like that, so you have to have a bigger pattern size, right? Like it should have, because 24, you have to compensate that, right? So you have to have some 1.4 side and some 2.9. No, this will be a pattern, right? The pattern should be very because if you put this pattern only after shrinking, you get this, right? Right?
Yes, sir.
Yes. So, and liquid and solidification shrinkage is maximum for aluminium, and which requires more riser volume. So these are all a simple solid shrinkages, but liquid and solidification shrinkage is AB and BC, right? Line AB and line BC. So that is maximum for aluminium. So you need more volumes of riser. So I'll tell you that riser when I'm coming to that. We'll discuss about riser. So you have to have huge amount of volume of risers to make sure that aluminium is done proper. Okay, fine.
Sir,
Let's
1 minute, sir. Can you give 2 minutes for writing the notes?
take your time, write it. But anyways, I'm sharing the slides. But anyways, if you want, you can write, or if you want, you can take a screenshot of.
Sir, would the shrinkage depend on type of steel also? No, sir. For iron carbon steel, there are different
Yes,
compositions.
because it matters. Like if your percentage of carbon is increasing, then there'll be some
Shrinkage will be more, sir.
yes, percentage of carbon is increasing, shrinkage will be little less. Carbon, because very hard material will be formed. If your carbon material is increasing, the structure becomes very hard. So the shrinkage is a little lesser compared to the less carbon, because if you're having less carbon, then the shrinkage happens more generally. So just write it fast, or if you can take a
Yes, sir. 1 minute, I'll write it, sir.
write it.
One
Okay,
minute.
fine. Write. If you want to write, you can write. But anyways, I'm sharing the slides. Don't worry. You write it.
Yes, sir. Yes, sir. Done, sir.
Done it? Okay, fine. Let me. And this values, what you're having here are only approximate values, not exact values. Sometimes
Exact
you can
value.
see different values. Don't worry about it. Okay. Just to get a feel, I got some values. Next, I want you to try this problem, but let me explain the problem to you, and I want you to try this problem. Just it doesn't matter whether you're getting a wrong answer or you're unable to follow it. And please, I mean, as it is a first question, I want you to try to give it try, so that if you give it try, you just think in a different ways, and after you think in a different way, when I say the solution, that solution will be strong and bound to you very fast. That's why I just give time to each and every problem before me solving it. So
Yes, sir.
okay, but as it is a first problem, I'll just discuss and explain what the question is. Okay, so here he's asking what a cubical casting of 50 size undergoes a volumetric solidification shrinkage of 4%. Solidification shrinkage, which line? A, B, B, C, C, D, which line? Which line, sir?
Sir, solidification is BC, sir.
BC.
Base.
Good. And volumetric solid contraction means solid shrinkage. Solid shrinkage is which line? Which line?
CD.
CD. Good. So AB is 4% shrinkage, CD is 6% shrinkage. There is no riser used. I mean, obviously, who will compensate solidification shrinkage? Who will compensate that? Riser, right? I told you, right? If you go back, I told you that, oh, yeah, sorry, this is, the slide I have to combine, but I'll show you that. So this solid shrinkage will be compensated by pattern, and this will be compensated by riser, but there is no riser, and pattern allowances is not considered. Even pattern allowances also is not considered. Riser also is not used. It means that obviously your canal casting will be compressed or not. Yes or no? What I'm saying, what it means that when you're pouring liquid metal here, as you're not using riser and whatever pattern allowances, your casting will become small, right? So now the question is, what is the final size of the casting? So it is having initial size how much? So let me draw the diagram for you guys again here. So this is your diagram here, something like this. So you have this, this, and this. So this is your point A, B, C, and D, and this is your TP, and this is your TF, and this is your TA. So here he says it is 4% of shrinkage. Here he says 6% of shrinkage. So what I say is here, let me say that. What is the volume of material? Volume of material at B? Anyone? What is the volume of material at B? When you,
it depends if cubical, okay, A cube.
A cube. So
S cube.
S cube, whatever. A cube is fine enough. So volume of material at B, right? How much is this? It is 50 cube, right or wrong?
Yes, sir. 50
cube mm cube.
Yes, sir.
Right. So what will be the volume of material at C? Huh? Volumetric shrinkage only, right? Everything is volumetric. So we have to percentage on volumetric. How much is that?
At C also is almost the same only, sir.
No, 4% is 4%.
Yes, sir. So it will be 96%, sir.
Right. So it is 0.96, right? Can I write that?
Yes, sir.
0.96 into 50 cube. Can I do that? Right or wrong?
Yes, sir.
Now again, volume of material at D. How much is that?
0.96 into 0.94.
Point
96 into 0.94.
0.94 into 0.96 into 50, right? Right or wrong? Who told this 0.94 and 96? Who's that? Who told this?
Shiva, sir.
Shiva. Good. Excellent. Why? Because at this point you have, at C point you have 0.96 into 50. Again from C you have 6 more % shrinkage happening from C. So that's the reason you reduce 9. So from C you are left with 94%, right? So 94% is 0.94 into 0.96 into 50 cube. So now let me write that A cube. So I want to find out the final size of the casting. What is the size of the casting? A cube is equal to 0.94 into 0.96 into 50 cube. Can you tell me what is the value of A, sir, here? Tell me what is the value of A cube. Tell me what is the value of A cube.
1 minute, sir. 1 minute, sir.
Please do that.
One to 800 mm.
What? 112?
800.
Okay. 112 800.
That is
So
meter cube, sir.
I can remove my cube root here. Can I put a cube root here?
Yes, sir. A will be okay. Sorry.
A is how much? Anyone? Cube root of this?
1 minute, sir.
Okay, fine.
46.47, sir.
46 or 48? 48.32 is answer.
48.31.
31. Okay. So approximately, according to my answer, it is 48. Cube root, not square root. Cube root is 48.32 mm. Approximately. Let me put the box in a different color so that to signify the solution. Yes. So that is the final casting value. Okay, sir? Any doubt in this till now?
No, sir. No doubt, sir.
Good. So let's go into different things. Now, so as I told you, as I told you, gray cast iron is an exception, right? So let me take this in. So by cooling gray cast iron, there is a possibility of expansion of material due to conversion of carbon into graphite flakes. That is, by cooling gray cast iron, your structure of BCC is changing into HCP. BCC means body centered cubic. HCP means hexagonal closed packing. Okay, I'll be discussing this atomic structures in material science when I'm discussing crystallography. But anyways, BCC represents body centered cubic structure. HCP represents hexagonal closed packing structures. As there is a structural change, the atomic structure itself is changing while cooling. What is happening? There is an expansion happening. Generally, by cooling, it should compress or it should shrink, but gray cast iron will be expanding. So, it means that you have negative shrinkage, right? Negative shrinkage is what? It is expanding. Negative shrinkage, I can say. This means what? Expansion is happening. Expansion upon cooling. Right? So to overcome this, size of the pattern will be reduced by considering negative shrinkage allowances. So now with this information, we have solved this problem one. With this understanding of this problem and with understanding of this gray cast iron, can you solve this problem? I'll give you 2 minutes. Please try to solve this problem and let me know. And now here I'm telling again, a gray cast iron bulk dimension so and so, so and so, so and so. The pattern making allowance is 1%. So here it is not volumetric, as he is not mentioning any volumetric allowances. The allowances will be on each side. This 1% of whatever is there, that will be allowances on each side, not volumetric. Please remember that. And now solve the problem. Again, repeat, allowances are provided onto the each side, not volumetric. If you have any silly doubt also, you can ask me. I'm here.
$1.03.
How much?
$1.03.
What are you doing is a pattern. What is the volume of pattern you're getting, sir?
2 into 10 power 5 millimeter.
That is volume of casting, right? That is volume of casting. So you're giving allowances to pattern, right?
Into 0.99.
No, it is not volumetric. That's what I said. No, it's not volumetric.
200, 198 into 99 into 0.99.
199 into. It's not 188.
One-
Man. 198.
198. 198.
198 into
99.
99 into 9.
0.9.
0.9.
So how much is that value? Tell me that. So 198 into 99 into 9.9. How much is that? How much is 198 into 99 into 9.9? Hello?
Point 0.97.
0.97, right?
Yes.
Yes. So you told some 1 point something. Where did you make mistakes, sir?
I took the pattern wrong.
Huh?
The pattern and the answers wrong.
Pattern?
I added the lines.
Okay, fine. I'm not getting your point. Anyways, your answer is right, Dinesh.
It will be
Let's-
9 point, sir, volume of casting will be 198 into 99 into 9.9, no, sir.
Yes, volume of pattern, not casting.
Casting, sorry, casting.
No, pattern. Okay. So what is this? Let me solve that. Again. So what is this? You can see it is 200 into 10 into 10. So it means that you want the casting size. What is the volume of casting?
Oh, sorry, wrong, sir, volume of pattern only, my mistake. I
Yes.
read it wrong.
Yes, volume of casting. I can write that as VC, capital VC is 200 into 100 into 10, right? So if I draw a diagram, this is 200, this is 100, and this is simply 10. 200, 100, 10. Okay. So volume of pattern. So should I increase the value of pattern? Should decrease the volume of pattern here?
We should decrease the volume of pattern because it's
as it is,
grass.
as shrinkage is, as it is expanding, right? So pattern should be less. So that is here. So 200 minus 1% of 200 is what? 2, right now?
2.
Into 100 minus 1 and 10 minus into 10 minus 0.1.
1.03, sir.
So this will be 194. I can't do my calculation. If it is wrong, please let me know.
194059.8.
59.8. So he's asking what is the ratio of volume of pattern to the volume of casting?
200, 2 into 10 power 5.
Okay, let me write volume of pattern as VP. VP divided by BC is asking, that is 194,059.8 divided by 2000. I mean, 2 to the 10 to the power of 1, 2, 3, 4, 5, right?
1.03.
0.97, right?
Sir, 1 point, okay, sir, they asked volume of pattern to volume of casting.
Yes. Right now?
Yes, sir, sorry.
So this is the answer. Got the point, guys?
Yes, sir.
Yes.
தெரியும்.
Okay. Fine. Let's go to the next elements. That is what is your draft or taper elements. Okay. Draft or taper elements. So what is this? For easy removal of pattern. Okay, let me draw the diagram first so that you'll be having a very nice understanding of that. Let's say this is your molding box, and you have a pattern put like this. Okay, and you have some sand particles like this. Okay, so this is cross-sectional view. Just I'm making cross-sectional view here. So this is your pattern, and molding sand. Green color is molding box. Now, you after ramming, you have to remove your pattern. Am I right or wrong, sir? You have to remove the pattern, right? Hello? Hello?
Yes, sir. We have to, sir. We have to, sir.
We have to remove the pattern, right?
Yes, sir. We have to remove the pattern.
The pattern, what will happen at this edges? Something will happen, right?
It will break.
No,
It will distort.
it will distort, right? You have some, it will become something like that, right?
Yes, sir.
Oh, so your molding sand should be something like this, like your cavity should be something like this, right? But instead of that, your cavity will become like this, right?
Sometimes it will break. Even if we take it by less force also, you will see a distortion.
So you can see that something, something happened like this, some breakage, something will happen, right? Like this, it will be there, right? Instead of a flat one, it will be, your cavity will be like this. So you don't want this breaking to happen, right? You don't want the sand to get disturbed. So to
Yes,
make
sir.
sure you get the pattern easily, you do that allowance. You make some allowance onto the pattern. That is like you make your pattern like this. So this is your upper portion. Just simply you make like this. You just make little taper. I mean, I'm exaggerating things here, but it will be a negligible taper. Okay, you can't see that with your naked eye if it is a large size casting. You make a taper. So this is your cross section. So this will be your theta. This is your height h of pattern. So, and okay, let me this theta and this whatever, sorry, this is your x. So x is equal to h and theta, and this theta varies from half degree to 2 degree, very minute values will give. So if you give this taper, now you can remove the pattern easily. That is what is called your draft or taper. You're providing some taper. So just read that. For easy removal of pattern from mold, on vertical surface of the pattern, draft or taper allowances are provided. This will depend on vertical height of the pattern. Why? Because this x value is depending upon the height and theta, right? So it will depend upon the vertical value of the pattern. So based on the vertical value, you provide this theta. That is what is called what? Draft or taper allowance. Okay, sir?
Okay, sir.
Okay, it's almost 11 o'clock. I'll give you 2, 3, 4 minutes. I'll be here because we can discuss the next topic tomorrow. I mean, not tomorrow, evening. So if you have any doubts in today's lecture, you can ask me.
Sir, in the numerical thing, if we have to For pattern only compensates solidification process. Sorry,
Solid.
only solid,
solid.
not solidification.
Solid.
Sprue will compensate the
Sprue,
liquid
not sprue,
loss,
riser.
liquid and solidification.
Not sprue, it is riser. Okay.
Riser.
Liquid and solidification, both. Yes.
Yes. That's that only, sir. To be clear with that.
Yeah. When I discuss the riser, you'll clearly understand why that riser is compensating and all. We'll get that point.
Yes, sir. And in the except for gray cast iron, mostly everything is positive or zero. If it is zero, then ratio will be 1.
Yes.
If alpha is 0.
Obviously, if alpha is simply 0, there is no change. The pattern will be exactly to the size of metal casting. No need of, because there is no expansion, there is no compression, right?
Yes, sir.
Yes. Dinesh, Deepak, Shiva, any doubts? Any doubt? No problem. Silly also no problem. Hello, Dinesh, Deepak, Shiva, are you here?
No doubt.
No doubt. Okay, Shiva is nodding, no doubt. Dinesh,
No doubt, sir.
thank you. Deepak?
No, sir.
Okay, Deepak. Okay, anyways, all the 4 guys, I'm happy so that we have just made our first session here. And let's meet in the evening. I think the timings, let me check.
No, sir. There's no evening slot for us, sir.
There is no evening slot?
No, sir. Only morning slots.
Is it like that? Let me ask your.
That's
Okay.
what.
8 to 9.
Okay, I'll just contact, they'll let you know. Your institute admins will let you know whether there is evening class or not. I'll just ask.
Yes, sir.
I'll just ask them. Let me see if there is evening class. If not, no problem. Only morning is fine for us. Okay?
Thank you, sir.
Okay, thank you all. Have a good, nice day. Let's meet tomorrow.
Yes, sir. Thank you, sir.
Okay.
Sir, evening slot is 8 to 9:30, sir.
Is it there?
Yes, sir.
Maybe I'll ask them because 8 to 9:30, I think for me it is a problem. So is everyone here? Is everyone here? Oh my
No,
God.
sir. Suraj went.
Suraj left. So the thing is it possible for you guys if I discuss it from 7 to 8:30 is fine for you? If I discuss that because 8 to 9:30 is little late for me.
Sir, even little earlier also is fine, sir.
Huh?
Probably around 6 o'clock.
Huh?
Around 6 o'clock, is it fine, sir?
If you want 6, I mean, actually, see, my work. I mean, I have to work in lab, right? So I'll come back to my room at 6 o'clock. So it takes some time for me to fresh up. So can we start at 6:30, something like that? If possible, 6:30 to 7 in between, something like that.
All right.
Hello.
Yeah, fine, sir.
Okay, so let's make it either 6:30 or 7. I'll just talk to Kumaran sir and I'll just tell him that. So they will inform you. Okay.
Sure.
Okay. Thank you, Shiva, Dinesh, Deepak, everyone. Thank you. Nice. We'll
Thank you.
Okay.
Thank you, sir.